Hello again, chemistry students. We're ready now to move on to our next topic in our discussion on solutions. Today we're going to be looking at factors that affect solvation. And so we'll need to obviously define what solvation is. A few things we'll be looking at today. What intermolecular forces affect this idea of solvation? What is solubility? And what factors affect it? We have some vocab that we're going to define, but we'll make sure that we go through all of this then today. And so let us go ahead and get started. All right. Let's say, for instance, you have some normal table salt. And so remember that table salt is sodium chloride. And so remember that's NaCl. In a salt like sodium chloride, we have what is known as ionic bonds. And so remember, we have positively charged sodium ions, negatively charged chloride ions, and so remembering that opposites attract, we then have our salt crystal. If, however, we introduce a polar substance like water, we can, depending upon how much water we add, actually cause a disruption of the salt crystal. And so the ions within the salt, for example, will become solvated, which means that they're going to be surrounded by the solvent. If the solvent is water, which oftentimes is the case in biology, we can say that the ions are hydrated because, again, the word hydro refers to water. The intermolecular forces that are at play here, therefore, are ion dipoles. So we have our ions here. Notice that sodium as an ion is positively charged. Water, the oxygen atom has a slight negative charge, and so notice that the water molecules are all surrounding the sodium ion, and so again, opposites attract. Conversely, if we look at the negatively charged chloride ion, we'll see that the water molecules, this time the slightly positive hydrogen atoms within the water are going to be orienting themselves around the ion, the chloride ion, and then notice because of these ion dipole forces, then these will not interact as well as they did before. We're going to go ahead and talk about different degrees of saturation. And so we're going to be talking about three different types of solutions. All right, the first solution we're going to talk about is called a saturated solution. A saturated solution is when the solvent holds as much of the solute as possible at a particular temperature. So temperature will affect the degree or amount of solvation. We can also say that if there's any undissolved solid, it's going to remain in the flask. And so again, we refer to this as a precipitate because it falls out of the solution. The dissolved solute is in a situation called a dynamic equilibrium with the solid solute particles. So let me go ahead and explain what that means. So remember, during the process of solvation, we have, for example, the water molecules are ripping apart the salt crystal, so the sodium ions are separated from the chloride ions. Sometimes, however, if these particles get close enough, the ionic forces will overpower the ion dipole forces, and it will again form the solid down here. And so this going from here to the solution, or this coming back together to form the solid, this is referred to as a dynamic equilibrium. And so the rates of these are the same. We can also have a situation where we have an unsaturated solution. So un means not. So this is not saturated. So what this also means is that we have less than the maximum amount of solute for that temperature is dissolved in the solvent. And so we could add more and it would still be able to go into solution. And so because of this fact, we will see that there is no solid that remains behind. So there is no precipitate in an undissolved or unsaturated solution. We can also have a very interesting case, the third type of solution, which is called a supersaturated solution. Super in this case means above, and so I like to think about like Superman flying above the streets of Metropolis looking for crime to stop. And so a supersaturated solution is when the solvent holds more solute than is normally possible at that temperature. And so rather than getting into the details of that, let me just say that it has to happen under a very tight conditions. If, for example, you have your supersaturated solution here, you have a single crystal, you place the crystal within the supersaturated solution, and it all falls apart. So it's going to then go back out of solution. And so you can also achieve this effect by scratching the side of the container. So it gives it a place for the solute and the solvent to latch onto, and therefore it's going to come out of solution. And so just by adding a single crystal. So this obviously is a very unstable type of situation. All right. There is a saying or axiom in chemistry. So as we said before, we know that opposite charges attract. So positively charged cations are attracted to negatively charged anions. And so that is one type of saying. There's another one that chemists use when they're talking about solutions, and that is that like dissolves like. And so what I mean by that, we have polar substances and we have nonpolar substances. And so if you take a polar substance, it's going to be able to dissolve very easily in another polar solvent. However, nonpolar substances would not be able to dissolve very well in a polar solvent. However, nonpolar substances will tend to dissolve easily in nonpolar solvents. So polar, nonpolar, like dissolves like. And so the table over here, we can see, for example, that as we increase the size of the hydrocarbon chain here, the solubility becomes less and less because we're making this more nonpolar. This hexane, which is a nonpolar solvent, as we increase the nonpolarity, you'll see that it goes very easily into solution. So again, as the nonpolarity increases, the solubility in a polar substance like water is going to decrease, whereas it will increase in a nonpolar solvent. And so that is how that works. All right. It's important to realize that the stronger the intermolecular attractions between the solute and the solvent, the more likely the solute will dissolve. And so this kind of goes back to what we just said about like dissolves like. A good example of this is ethanol. And so ethanol and water. And so we have, for example, because we have the presence of both hydrogen and electronegative oxygen, we have hydrogen bonds, we have also dipole-dipole forces, and we also will always have dispersion forces no matter what. We also note that ions in water, as we discussed at the beginning of today, also have ion-dipole forces. So notice the H bonds are the strongest of the intramolecular forces, and therefore it's going to make ethanol very easily to dissolve in water. I want to now turn our attention to what happens if we try to get a gas in the solution. And so a very common example of this is carbonated beverages. And so by adding carbon dioxide to pop, you can give it that fizz, and so it will also help to improve its flavor. In general, the solubility of gases in water will increase with increasing mass. And so we have a table over here, which of course you don't have to memorize, but if we look, we'll see that the nitrogen gas as the smallest atomic molar mass, this would be roughly 28 grams. Krypton, a noble gas, has an approximate molar mass of 84 grams per mole. So the masses increase as we go down. Notice that the solubility in terms of molarity, so again, just as we talked about yesterday, molarity is the most common way we express concentration in chemistry. Notice that as we increase the molar mass of the gas, it also causes the solubility to increase as well. And so this trend holds true. Why is this then? It's because the larger molecules have stronger dispersion forces. And so, as we just said in the previous slide, the stronger the intermolecular forces, the more easily the solute and solvent will dissolve. All right. We can also see that by increasing the pressure above solution will force more gas to dissolve. And so the reason hopefully should make sense. You're causing the gas particles to get closer to the liquid, and therefore they don't have any other place to be, and therefore they're going to be able to dissolve more easily. And so we can see, and if we remember back a couple chapters and we're looking at the states of matter, liquids are somewhat compressible, solids are virtually incompressible. Therefore, the solubility of liquids and solids does not really change appreciably with pressure. So we only see this with gases because we know that gases are highly compressible. And so the relationship between solubility of a gas and the pressure was first described by a scientist by the name of Henry. And so we're going to talk about this in just a second. The solubility of a gas in a liquid is directly proportional to its pressure. And so we can see that Henry's law describes this. And so this is going to look a lot like one of the gas laws that we had in our previous chapter. S1 over P1 equals S2 over P2. So S is the solubility of the gas. P is the partial pressure of the gas above the liquid. And so there might be a problem on the next test, or most likely will be, that involves you calculating using Henry's law to calculate either the solubility or the pressure of a gas. And so I would have to give you three of the numbers, and then just like in the last chapter, you can then solve for the fourth number. All right. As I mentioned before, when we're looking at saturated versus unsaturated solutions, we mentioned that temperature is a factor that is involved with how well solutes go into a solution. This here is a set of solubility curves, and so for the test you will not need to worry about interpreting this, and so this is different from the phase diagram. Notice that on the horizontal scale we have temperature in degrees Celsius. It's increasing as we go to the right. The solubility in this case is expressed as grams of salt in 100 grams of water. It increases as you go up here. And so we can say, generally speaking, that the solubility of a solid in liquid solvents tends to increase with increasing temperature. And so hopefully this makes sense, because basically by increasing the temperature, you're adding heat to the solution, it causing the molecules to bang around the container, hit into each other more frequently, and therefore there's more of a chance for them to interact. And so, for example, if we look at, let's say, potassium chloride, we can say that at 50 degrees Celsius, we're going to find out that we're going to see roughly 42 grams of salt of the potassium chloride is going to be able to dissolve in 100 grams of water. And so notice that the curves are different depending upon the salt that you're looking at. I want to, however, point out the opposite is true for gases. So higher temperature will actually drive the gases out of solution. And so if you're at a bottling plant for pop or something like that, it's important that you don't leave the gas or the pop out too long in the hot summer weather, for example, because that will basically cause the gases to come out of solution. So the carbon dioxide will come out of the pop, and the pop will lose its fizziness. And so this is another reason why people tend to either chill their pop, therefore it doesn't lose its fizziness. So again, the temperature will cause the gases to be driven out of solution. You can see this from this graph over here. And so, as I just said, carbonated soft drinks will remain more bubbly or fizzy if you keep them in the refrigerator because it's colder. if, for example, you go and visit a campground or something over the summertime, you will see that the warm lakes will have less dissolved oxygen gas in them than cool lakes. And so obviously that would have an impact on the ecosystem of that particular lake. And so, all right. And so with that, we're going to stop here then for today. And so go ahead and please do the problems for this section. And so we have one more topic to discuss. And so I hope to talk with you, and I'll talk to you guys a little bit later. Thank you.